In a previous video, we built this second order active low pass filter, and I've also just knocked something out of it there. But we built this circuit, and in this video, we are going to connect it up to, in our case, a USB oscilloscope, and we're going to take some measurements. And we're going to take measurements at different frequencies. And based on those measurements, we're going to start to assemble something called a Bode plot, which we'll do manually. And we're going to explain the different steps of how to do that. Now, I'm using, just like in a previous video, a USB oscilloscope by a company called Pico. This is the base model Pico scope. It's a 2-channel oscilloscope with a signal generator. And so what we're going to be doing is we're going to be using this to, first of all, supply signals of different frequencies using the signal generator. And we're going to measure the input and the output respectively. So if you watched our previous video on the transistor amplifier, you'll be familiar with how we connected all this up. But we're going to do something similar in this video. If you're not familiar with oscilloscopes and leads and connections and stuff like that, very simply, we have these scope probes which are connected coaxially like this with a sort of twisting locking mechanism. And the other end of the scope probe looks something like this. We've got a retractable sort of spring-loaded hook mechanism that we can use to clip onto components for measurement purposes. And those measurements are made with respect to ground or to zero. And so this is our ground connection as well, which is sort of tied on to each probe. So what we're going to do is, first of all, we've got those 2 channels on our oscilloscope, both of which have leads like this, but we're going to connect our actual signal generator first of all, which is a tiny bit different. What I've got is another coaxial lead there in that signal generator channel, but it leads instead to these crocodile clips. And so what I'm going to do is I'm going to connect the crocodile clip to the input of our circuit here. And so when we built this circuit in the previous video, our input was defined as that kind of leg of the first resistor sticking out there. If you've not watched the first video where we put this circuit together, it might be worth doing so. Relative to ground, so the black connection here is going to ground. Now, what I've got here is a ground rail, which is the second bottom row. That's our 0-volt rail that we defined in the previous video. And I've only got one poor capacitor here that's going to have to be doing a lot of work in this video, I think. But I'm going to connect it to that capacitor leg there, because that's connected to the second bottom row in this circuit. Hopefully, if I bring it up a little bit closer, you may be able to see. Though I've just popped out a resistor there, so I'll stick him back in. So now we've got our signal generator connected, we can start to apply signals of different frequencies to this filter circuit, and we can see how the behavior or the attenuation of this circuit changes as the frequency increases. That's the idea behind what we're doing today. But we need to take some measurements in order to do that. And what I want to do is I want to record measurements of the output relative to the input. And so I need to record both. So here's my channel 1 oscilloscope. So channel 1, you'll see it's color-coded yellow in this case, and here's my corresponding yellow lead. It's a 10 times probe, just make sure it's set to 10 times. And I'm going to clip that onto the input as well. We're measuring the input. Again, I'm measuring relative to ground. I can clip this on that poor capacitor as well, or if we're running out of space, I could just put a sort of dummy lead into that second bottom row and connect it to that. It makes no difference for our purposes, or it shouldn't do really. Likewise, we're going to connect the output of our circuit to channel 2 of this scope as well. So if I can find it, here's channel 2. It's a red connection to correspond with the red on channel 2. And we're going to apply that to the output of our circuit here. Now, just recalling the pinout from our previous video for this operational amplifier, the output was in our case pin 6. And so what I'm going to do again, I'm just going to sort of add a little dummy connection in here to pin 6. If we can squeeze it in here, have we got room? Put that in there. Pin 6, we're going to just have this free floating connection for now. And all I'm going to do is I'm going to connect the scope probe for channel 2, which is this one here. I'm going to connect that to here, and hopefully that's not going to go anywhere. If you do encounter problems with that, what you could do as well is just connect a resistor. So if I take just any resistor, let's lose that, and connect the resistor in place there. Now that resistor, I'm not bothered about the resistance or where it's going, because I'm not even going to use the resistor. I'm still going to clip it onto that side of the resistor. So I'm going to put that there, if I can. And there it goes. So this resistor is just acting as a sort of dummy component that's not doing anything. That's just sitting, going from pin 6 to nowhere really. I'm just using it as an anchor to connect that scope lead to that scope probe. I'm losing all of these battery snaps, so I'm going to leave them out of the way for now. Okay, so again, that's relative to ground. I'm going to use this dummy connection that I've used for a previous ground connection. That's going to go on there as well. And we'll just keep that out of the way. So there's our input and output measurements in place there. What we're now going to do is use the software to apply some different signals from the signal generator and measure those inputs and outputs respectively. Before we do that though, I'll remember to attach our battery snaps back in place. So again, recalling the previous video, it's a dual rail power supply, so we have positive to negative on the second, or to 0 on that second last row, and then we have positive in that second last row to negative on the row below, and that's going to give us a -9 volt rail along the bottom. So we have a dual rail supply now, but more information about that in the previous video. I'll connect up some batteries and we'll start up the software. So I've opened up the software here, which is Picoscope 6, which comes with the Picoscope 2000 series that we saw just before. And there's a little bit of setup and installation involved, but basically once we're all plugged in and the scope is connected to the computer via the USB lead, and we're opened up the software and all that kind of thing, we see something like this. So at the minute, nothing much is going on. And we're going to do a few things just to get set up in order to start taking some measurements for this filter circuit. So first of all, it's a 2-channel scope. We're using both channels. By default, channel A is on auto, channel B is off, so we are going to switch that to auto. And also by default, they're set to DC. We're measuring AC waveforms. We're going to apply an AC waveform to the input and the output, so we're going to set those both to AC as well. Speaking of our input signal, we said that the scope has a signal generator. It's controlled by this button here. So if we open this little box here, we get this drop down. And what we can then do is control the signal that we're going to supply to our circuit. So what I'm going to do, first of all, I'm just going to make this a sine wave. I'm going to leave this as 1 kilohertz for now. I'm going to leave the amplitude at 1 volt. And we're going to switch this thing on, and all of a sudden we get something going on here. It looks like a bit of a mess, but luckily for us we have this button here, the little lightning bolt, which is our auto setup, and we click that, it has a bit of a think, and then we get something like this going on. So what I'm going to do next is I'm going to take a look at the very bottom of the screen here. We have a trigger setting, and so basically this is sort of like free running waveforms that pass through the circuit and they're measured in real time. What I'm going to do is I'm going to set the trigger to auto at the bottom, and that's going to try and sort of identify a sort of fixed point, which is marked on here, as the sort of start of the waveform, and it's going to settle things down visually as we look at them here. Okay, so what we have now is we have two waveforms. We have channel A and channel B, and they correspond with the blue for channel A and the red for channel B. Now, one thing to bear in mind is that these have separate, or they can have separate scales. So down the left hand side we have the y-axis scale for channel 1 or channel A, which is going from 0 to 200 millivolts by the looks of it. And on the right hand side we have channel B y-axis scale going from 0 to 100 millivolts. So it's a bit misleading because at a glance it looks like the output is bigger than the input, but it's not. So just to bear that in mind, because what we're seeing hopefully in this circuit is attenuation. It's a filter, and so because it's a low pass filter, as we increase the frequency, what we're hopefully going to see is the output decrease. So bigger the increase in frequency, or the larger the frequency gets, the smaller the output's going to be. It's going to have greater attenuation. So we can see that very quickly just by increasing our frequency here. We can just click to start going through 2, 3, 4. You'll notice it's rescaling, but now notice that the right hand scale goes to 50 millivolts only. So this y-axis scale might resize. It's fairly consistent here, but we can see that the output is getting smaller and smaller as we increase the frequency. So that's the idea behind our low pass filter. That's what we expect to see. As the frequency gets bigger, the output is going to be attenuated. Now what we can do in this software, which we're not going to use, but I'm going to show you how it works, is we can have what's called a frequency sweep. And we can do that by ticking this sweep mode here, and it goes through all of those frequencies automatically. So you can see here we're starting at 1 kilohertz. Let's say that we want to go up to, it goes up to 2 there. Let's say we want to go up to, I don't know, 50 kilohertz, say. And we're going to do that in increments of 10 hertz is very small. We'll do it in increments of 100 hertz. And we'll see something like this. It's rescaling quite quickly, but what you can see, hopefully, let's increase the time between them. And let's maybe increase that interval again to 200, say. What we're going to see is something like this. As the frequency gets bigger, the waveforms become much narrower and narrower. In fact, let's just extend that division a little bit so we can see a bit more clearly. The narrower the waveforms get, they're increasing in frequency, but notice the amplitude of that output, the red, is decreasing as the frequency increases. And so what we want is to produce what's called a Bode plot, which plots the frequency response across the whole domain of the frequencies that we're going to measure. Now, Picoscope does have a spectrum mode, and I'll show you what that looks like if we click on this. So the spectrum mode is actually analyzing all of the frequencies that we're measuring through the course of that frequency sweep and plotting a result, and it's in decibels down the left hand side, and then we have our frequency going along the bottom. Now by default that frequency along the bottom there is going from 0 to 10 megahertz. The scale's in megahertz in the bottom left there. And so remember I think we set it to go from 1k to 10k. So we're measuring in this tiny little range on the left. All of this is just noise, and so I don't want to see that. Rather than looking at 10 megahertz, let's knock that down to, let's say, 12 kilohertz. And what we're hopefully going to see is something that's starting to look a bit tidier. The problem we've got now is that the sensitivity is still way too high. And so what I want to do is just edit a few things. We have this mode here called spectrum options. And I'm going to decrease the number of bins. The bins are kind of what you think of as the amount of data that we're looking at or trying to collect. This is way too much for our purposes. We're going to decrease that way down there. And what we're also going to do, because you can see the sweep is going up and down, you can see that sweep taking place from roughly from 1K up to 10K and back. We're going to change this to where is it? Sorry, rather than the magnitude, which is just the measurement at any given point, I'm going to change this to peak hold. And what it's going to do is it's going to start to kind of work out the peak average and retain that average over time. So over time, it's kind of going to build up more data and hopefully start to put together a clearer view. We're not sweeping very far actually, so what I'm going to do is I'm going to change this to go from, where were we going? We were going up to 50 kilohertz. Let's go up to 100 kilohertz. And let's also change this view so that we're looking at 100 kilohertz worth on the x-axis as well. 98's the closest. Let's go for that one. So now you can see along the bottom here we're going from 0 to roughly 100 kilohertz. Now this is starting to get a little bit more informative. You can see that it's taken a while just to gather the data, and every sort of pass of the frequency sweep, the data kind of is improving. The lower the number of bins, we changed the number of bins before on this spectrum options. The lower the number of bins, the quicker these results will be gathered. The higher the number of bins, the more detailed. And so it's kind of a trade-off really. But what we're getting is, hopefully we can see this kind of attenuation take place. Here's our input, and it's sort of tidying up over time. But here's our output, and as the output frequency increases, we're increasing the frequency along the x-axis, we're getting greater and greater attenuation in the y-axis. Now, the problem is this scale here in decibels is measuring with reference to an arbitrary value. Normally, the Picoscope software does something like references it with respect to 1 volt, for example, and it uses 1 volt as like the standard that it's measuring to. We don't want to do that. We want to do the output with respect to the input, and so we're not going to use this frequency mode there. It's worth sort of seeing, so you can sort of use it as required, but we're not going to use it in this video so much. We're going to actually rely on the typical sort of scope waveform view that we saw before, and we're going to take discrete measurements at certain intervals. So I'm just going to press stop on this for now to pause it. So what I want to do is I'm going to go back to the signal generator we had here. I'm going to turn that sweep mode off. And what we're going to do is we're going to take sort of manual measurements for a range of different frequencies. And one of the advantages of this is you can do this with any oscilloscope. You don't need a fancy sweeping signal generator. You can do this with a normal signal generator, a normal oscilloscope, and it's quite easy to do as well. So what I'm going to do is I'm going to start to take some values of the input and the output voltages at different frequencies. And so I'm going to increase, going from maybe say from 10 hertz. So I'm going to 10 hertz there. I'm going to start at 10 hertz. I'm going to leave the amplitude alone. All I'm going to be changing is this frequency. And what I'm going to do, I'll press start again at the bottom here, and the very first thing I'll do for all of these measurements is I'll use the auto set function. And so now we have our input and our output. Now remember, this is a low pass filter, so at very low frequencies we shouldn't expect any attenuation. And we can kind of see that here. The input and the output almost perfectly overlap, which is what we want to see, and they're on the same scale as well. So what we're going to do is we're going to take some measurements. Fortunately, in this software, it's nice and easy because there's a measurements option at the bottom. I'm going to add a measurement. From channel A, I'm going to record the AC RMS. Now, if you record the peak voltage or the RMS voltage or whatever, it doesn't really matter because we're going to be comparing one with respect to the other, the ratio between the input and the output. So as long as we're consistent, that's fine. Which section of the graph, we're going to measure the whole trace to get as best a result or as accurate a result as possible. So channel A, AC RMS in our case, OK. And it appears right down at the bottom. We have something going along there. And what we're going to do is exactly the same for channel 2. We're going to add a measurement, and we are going to add for channel B now AC RMS. I forget, just looking at these results, which are very small here, I remember something we mentioned earlier. We said that we set our probes to 10 times probes. Well, we've got to make sure that that's acknowledged in the software on the oscilloscope if you're using a manual oscilloscope. Here I can drop down channel A, and there's an option there. I need to make sure I'm using a 10 times probe. I forgot about that, which would probably tidy up some of that frequency work we had before as well. Anyway, channel B, same thing, 10 times probe. So there we go. Anyway, so now we've got our two sets of results, our two measurements down at the bottom. 698 millivolts or thereabouts for channel A, 700 millivolts thereabouts for channel 2. So pretty much parity between the two, which is what we expect between them. So what I'm going to do is I'm going to record those measurements, and for the input channel A and for the output channel B, I'm going to record those two voltages, and then I'm going to move on to the next frequency. So let's say the next frequency, again I'm going to my signal generator here, I'm going to change this to 100 Hertz say, and I'm going to do the same thing. I'm going to make sure I press auto set first. The best way to think about it is that this software is looking at the same image that you are to make its measurements, and that's the same with digital oscilloscopes on the benchtop as well. If the image looks bad, then the results and the measurements will probably also be bad. That whatever algorithms are working behind the scenes, they're looking at the same picture that you are. So it's best to use that auto set, get a nice clean image first. Here now we've got our two measurements. If they're sort of flickering too fast, then just press stop, and we've got them frozen there. There's an average result here which takes the average of the minimum and the maximum results that it's measured over the course of the trace. Now, to be honest, we'll find that there's probably not that much variance between them because it's a fairly sort of plain sine wave. But the average result you might want to use, which is just further along there. And what I'm going to do is I'm going to record a range of results over the course of several different frequencies. Let's have a look at what they look like. Okay, so what I've done is I've just put all these results in an Excel table here, and here down the left hand side you can see the frequencies that I've used. I've not been consistent in the sort of the spacings or intervals between these frequencies, but I've just tried to pick a range from 10 Hertz all the way up to 100 kilohertz or 100,000 Hertz. So I've gone up from 10, 100, 200, 500, 1,000, 2,000, 5,000, 10,000, 20,000, 50,000, 100,000. And at each of those frequencies, all I've done is what we said in the Picoscope software. I've taken measurements of the RMS of the input and the output signals that I'm measuring once I set each of those. It's a good idea to make sure you press that auto set button for each frequency to make sure you're getting some good measurements there. So I'm not really interested in the values of these inputs or these output voltages. They're entirely arbitrary depending on the amplitude of the input waveform that we supplied with the signal generator was a 1 volt waveform. And if that was bigger, then these would be bigger, and vice versa. I'm not bothered about these measurements in and of themselves. What I want to know is about the ratio between them using the decibel formula. And so we're going to get a gain column, which I've left blank here, but we're going to measure the gain in decibels across this whole range of frequencies. And hopefully we're going to plot a graph, a Bode plot, just in Excel, which hopefully anyone can do if you're following along. So to do that, we're going to use the decibel formula for the gain, and in Excel, because we're doing a calculation in Excel, it needs to start with an equals. So equals 20 times log to the base of 10, which is basically just log 10. You can see it in the drop down there. Log 10 for log to the base of 10 in Excel of the output over the input. So I'm going to click on the output to the left there, divided by the input, and I'm going to close those brackets there. So 20 times log to the base 10 output over input, and that's it. So for this first value it's 0 because the output and the input are the same, they're both 698. I've just recorded these to the nearest whole number, by the way, and I've not done a particularly accurate job. I just quickly went through and gathered those results, but you can get a little bit more precision out of that software than I've given it credit for. But anyway, because these are the same, 698 for both the input and the output, there's no gain one way or the other. If we are getting an increase in voltage, the output's bigger than the input, then our circuit would be an amplifier and we'd have a positive gain measured in decibels. The unit of this is decibels, I should say. On the other hand, our circuit's a filter, and what it's doing is it's attenuating or reducing the output relative to the input, especially as the frequency gets higher. And so what I'm hoping to see here is a negative gain. All this column should be negative because you'll see just even at a glance going down here that the output is smaller than the input, and it gets smaller and smaller as it decreases. So all I'm going to do is I'm going to grab the bottom right hand corner of that cell there, and I'm going to drag this down. It's going to repeat those calculations for the whole column, and what we get is hopefully something like that. You can see that that gain is getting increasingly negative as we go down. Towards the very end here it starts to creep up. It might just be difficulty measuring at those high frequencies with the oscilloscope that I've got. It might also be a limitation of the operational amplifier. When it starts to get to those high frequencies, it doesn't attenuate as well. The performance sort of drops off. I'm not too bothered about that, but for the purposes of what we've got here, this is looking nice so far. What I'm going to do is I'm going to plot a graph, and I'm going to plot a graph of frequency on the bottom and gain up the side. So I'm going to click on the header, the column header A, to highlight that whole column. I'm going to hold down Control, I'm going to highlight column D. So now I've got those two columns highlighted. I'm going to insert a scatter graph, and I'm going to choose the ones with the points and the line, the curved line there. And what we get is something that looks like this. I'll just give this a more sensible title. It's Bode plot, second order low pass filter. Okay, so a couple of things with this straight off the bat. What I want is a logarithmic scale on the x-axis here, and the reason for that is because this really is a log-log graph. This is a linear scale down the side, but remember that it's decibels, and decibels, we use log to the base 10 to calculate these values. So the logarithm down the side is already sort of taken care of, but the scale along the x-axis is still linear, and I want this to be logarithmic as well. Very easy to do in Excel. I'm just going to double click on any of the numbers on that x-axis, and it opens up this menu if it wasn't already open. And all I'm going to do is I'm going to choose the axis options from the menu there. It looks like a little bar chart, and drop it down, and we can tick logarithmic scale. And so now this is starting to look a lot more like a Bode plot that you might have encountered previously. Down the left hand side It's currently going in increments of 5, which is fine. But if I double click on that, I'm going to change that so that it goes in major units of 3. Because when we're looking at like 3 decibel, 6 decibel cut-off points and that kind of thing, it's probably more of a useful delineation to have going down the side there. Another thing I'm going to do is, back on this axis, I'm going to, just going back on the axis options, I'm going to choose the tick marks drop down instead. And I'm going to add, it could be any of these, it doesn't matter which, but I'm going to switch on the major and the minor tick marks. And now we have these sort of logarithmic scale markings going on for 5 cycles here. It's a 5-cycle graph. So what we have here, if you're unfamiliar with the logarithmic scale, is we have increasing in orders of magnitude of 10 each time. So from 1 to 10 to 100 to 1,000 to 10,000 to 100,000. We're covering the same range of frequencies, but we're doing it in this logarithmic scale to the base of 10. And within each cycle, each one of these sort of, say 100 to 1,000, that's a cycle. In each cycle, we have these minor tick marks that get closer and closer together, and they demark the multiples of the start of the cycle. So for instance, this one here, it starts at 1,000, that'll be 2,000, 3,000, 4,000, 5,000 and so on until we get to 10,000. In this cycle, it will be 10,000, 20,000, 30,000, all the way up to 100,000. So one of the things we spoke about in some of the simulations of the course materials that we run is the because this is a second order filter, its cutoff frequency is at -6 decibels. If it was a single order filter, it would be at -3. But because it's a second order filter, the cutoff frequency is defined at -6. And so all we need to do now is trace along the -6 decibels to where it meets the trace there. Just be careful, because what comes up when you hover over it, it's looking at the nearest point. It's referring to that point. So ignore this little pop-up here. I'm not too bothered about that. We should be tracing from there to the axis, and from the axis to the trace, sorry, and then from the trace correspondingly up to the horizontal axis there. And that looks roughly, to my eye, about 4,000 hertz, because 1,000, 2,000, 3,000, 4,000, roughly speaking. You can sort of make this bigger, and you could measure more points as well to get more accuracy. I've just measured a sort of handful there. Especially if you're looking to ascertain the cutoff frequency, you might want to take more readings around those sorts of frequencies to get more points in here and greater accuracy. But hopefully this video was useful to learn how to take measurements of the input and the output, just manually taking those readings at set frequencies, and then just using common software like Microsoft Excel to put together a Bode plot with a logarithmic scale that you can use as well.